Hi, everybody. Hopefully, I'm not, gonna put you to sleep. So I'm the last one. So my name is Ahmed Mahfouz. My project is about energy consumption optimization for data centers. I'm really interested in infrastructure engineering. That's why I chose to do something like that. Um, so the motivation here comes from the, data centers has been growing crazy, and the demand has been increasing. Even in the last 2 years during the pandemic, the demand has taken up. Video meetings became the norm. Zoom is there. TikTok is booming. So the U.S. Department of Energy even projected that in 2020, like almost 4% or 5% of the U.S. electricity will be consumed by data centers. So this is a big thing. That's why, and it's millions of dollars to run these data centers. And also because of the climate, also data centers became one of the important sources of greenhouse gases. So energy consumption optimization for data centers is a big deal because it touches two things: reducing cost and also trying to be environment friendly. So um, to find something that I can work on, this field is really very broad and very complicated. In terms because how to do that? What is exactly the problem that you're trying to solve? So I tried to find a research paper that I can follow, I can use, and implement. It was at the beginning, it was a struggle because I couldn't get my hand on any research paper. But being here for almost 3 years in George Mason, I've never used the university libraries, and it gives you access directly to IEEE for free. So I was able to get so many research papers that I was able to read, and finally I choose one that I can use for my project. The first one is like thermal. To be honest with you, the order is different. There's a one that was published in 2006. That the other one was built on top of it. So the one I used is the first one was the thermal aware energy efficient task scheduling for DVFS enabled data centers. I'm going to explain more what does that mean. But the stuff that has been built here is a continuation for the work in the paper that was published in 2006. So let's talk more. So we were talking about thermal aware energy efficient task scheduling for DVFS. So what is thermal aware? A significant portion of the energy consumption in a data center comes from the AC, the air conditioner, the one that cools the data center. Is a big portion out of the energy comes from that. The other one is the computation. So whenever you run anything on any server, the processor, the CPU that's running that computation also consumes energy. And we'll see how is that happening. So also the servers in the data centers, they are in a limited space. So they are kind of organized in racks in a compact space and produce heat. And the amount of heat that CPU dissipates when it's running any CPU intensive tasks, it's actually equal to the power it's consuming. So if we know the heat, how much heat it's producing or emitting or dissipating, if we can calculate that, we'll get to know exactly how much power the CPU is really consuming. And what is DVFS? Most of your machines always running on a peak frequency. So the CPU, whenever you go by a machine, it says the CPU or the processor is having that much megahertz. So, but in data centers, they have new things that they have been trying to use, which is called dynamic voltage and frequency scaling, where they can adjust the voltage and the frequency of the CPU. So I don't need to work on a peak frequency all the time. The task that I need needs that much frequency only, so I'm just going to adjust the CPU frequency by that much. Whenever they do that, why this is important? Because this is the relationship between a CPU frequency and power. The more frequency the CPU is running on, it's a Q function with the power. So the power is a Q function with a frequency. This paper is saying it's a Q. And it have a huge, there's a proof for it, and there's some simulation that it's used to prove that. So that's why, as you can see here, in the Q function, you start like the CPU, when you're using a low frequency, the is the power consumption is very low, but once you start increasing the frequency, it peaks, as you can see. So adjusting the frequency of the CPU is really very crucial to make sure that we are always running the CPUs in a cool mode and it doesn't consume that much power.
So if you increase the frequency 2 times, twice, you can do twice as much work, but you will consume 8 times more energy.
Exactly. So that's the problem. So yes, but that's why we need to make sure. So I'll come more. So okay. So how we optimize energy consumption? So the idea here, okay. So we want to make sure all of these. So in a big data space now and a distributed systems, we always break. Most of the work now we break down or break down a huge task into smaller tasks. Now we want to distribute these tasks efficiently across all the CPUs, across all the machines in the data centers, and then to make sure that all of the CPUs are running in a reasonable frequency without peaking any one of them, because at peak, you are, as you can see, that the energy consumption is increasing in a crazy way. So the idea here, how to optimize the energy consumption, is making sure that we are evenly scheduling the tasks across all the machines in an even way to make sure all of them are running on a reasonable frequency to reduce the energy consumption. So how we can do that, is it that simple? That's the question. So building that energy consumption optimization system, it requires building full models, not single models. Each one of them, so we have a task scheduling model, heat flow model, server power model, AC power model. So the task scheduling model, you have it's a binary matrix where we have the machine in the row side here, and we have the tasks that we want to run. So we have task 1, we want to run it on machine 2, task 2 runs on machine 3, and so on. So at the end, the optimizer, it will produce this or optimize this binary X matrix to make sure that the task is running on a certain machine and make sure that all the frequency across all of them and the power consumption is optimized. And there are some constraints here. We want to make sure that the task runs only on one machine. So if we added together all of the column here, the submission here will produce just one. That's the first constraint here. So when we add together, we want to make sure always that the summation here will lead to 1. 1 means it's running on machine 2, 0 means it's not running on that machine. The other constraint for that task, it requires certain frequency. So we want to make sure when it runs on that machine, it doesn't need more than the max CPU frequency, because that's the limit for us. We cannot just go beyond the maximum CPU frequency. So the other constraint here, J required is the amount of frequency a certain task needs. So all of the tasks running on a certain machine should be less than or equal to the maximum frequency of that machine. The heat flow model, which is the thermal aware part that this paper was really focusing on. Whenever we have an AC pushing cold air in, it cools the machine, and then the machine starts emitting from the fan and from all of our machine's fan a hot air. And that hot air, based on the CPU when it's running a task, it gets heated up, and that heat is equal to the power it's consuming. So also when the AC is pushing some cold air here, trying to cool this machine, but also other machines are, because of the limited space, whenever they are pushing out any hot air, it recirculates back into the machine. So we have an issue here where in a data center, in a room, the hot air coming from other machines will recirculate into other machines. So it will interfere with the AC air. So that's why you have an AC air getting into this machine, plus the recirculated air coming from other machines. And that creates for us a matrix here. As you can see, this is a matrix that they call it the correlation recirculation matrix, where it defines for that machine A11, this is the same machine, But 821, this is how much air we are getting from machine 2 into machine 1, and so on. This data is data that we don't really calculate. It's a generated data from the simulation when you design a data center. When you design a data center, there are some tools that are being used, something like called Autodesk, CFD, Fluid something. When you design a data center, you understand the air flow within the data center, and you understand exactly what is the correlation, recirculation matrix here, and you produce that out of the simulation, and then you use it in your model. And as you can see here, I'll try to summarize that. This formula is the second paper, the old paper that was published in 2006. It was just to produce this formula. So this formula, in a simple way, to calculate the power or the energy, it's the temperature multiplied by C, which is the heat capacity, which is how much energy you need to increase the temperature of a certain material, air, whatever, by 1 degree. Air density, which is how much, what's the mass of that air, and then the flow rate, which is the speed of, or how much air is flowing per second. So these three multiplied by the temperature will get you to know exactly how much energy is consumed by a certain machine. S here, as I told you, is a flow rate. So if this is S, which is whole flow going into this machine, if we subtract it from that recirculation coming from other machines, we'll be able to get to know exactly how much air coming from the AC. And that's the first part here. We are trying to subtract all the air coming from different machines into this machine. We subtract that from the whole airflow, and we will get exactly what's coming from the AC. And then this is the recirculated air power. So these together will give us the power for AC and the power from other machines. That will give us exactly the total power. So this is the second model, which is the heat flow model. The third model is the machine power model. And this is the one I was just talking about, that the power of the computation is a function of the frequency, and it's proportional to the cube function, the cube of the frequency. You can see here we have beta 1 and beta 2. These are constant. Beta 1 is any machine running, it has different other components, and all of them need some power. So there's some constant power that always there when you run any machine, aside from the computation. And then beta 2 also is another constant related to the type of the CPU. And also all of that, whenever you use a certain CPU, you can get this constant based on what CPU type you're using into this machine. The last one is the AC power model, which is the AC efficiency and how we can calculate how much power the AC is using. There's something called here, forget the name of this, theta, I think. Yeah, this was theta, correct? Yeah, it's this is what they call it is the cooling efficiency of the AC, or the coefficient of performance. It's equal to the power of computation divided by the power the AC is using. Also, theta is equal to how much temperature of the air, the temperature that the AC is supplying, multiplied by, what's that called? I forgot the name of the Latin word names for that, but this is gamma, I think, gamma 1 and gamma 2. And the temperature is between theta 1 and theta 2. It's a range at the end. You're saying in a data center, I want the temperature between 15 and 18. It cannot go more than that, or it cannot go less than that. So any temperature when the AC is working, you define a boundary for that temperature, and to calculate the efficiency of that AC is that way. So at the end, what they're trying to do is using this, like these formulas to deduct at the end that the power of the AC is the total power of the computation across all the machines, divided using this and using this, we deduct this formula, divided by gamma 1 multiplied by T supply and gamma 2. What is gamma 1 and gamma 2 is also, these are constants that you produce during simulation and fitting and understanding, and also used by the AC specs, the specs of the air conditioner. So at the end, what we're trying to do in this, we're trying to minimize the power computation using the control variable X and T supply. So these are control variables, and this is whatever we are trying to minimize, which is the power of the computations and the power of the AC, the consumption of the AC, the consumption of the machines to do computations. So this is what we're trying at the end to achieve. And that's it. That's the conclusion. So when I started working on this problem, I thought it's going to be easier than that, but it has been really, to understand the papers and the research papers wasn't that easy. It took me some time to just understand what they're trying to say, and reading more than one paper, because they are built on top of each other. Sometimes you feel that there's something missing, and they refer to something within the paper that was in the previous paper. So you have to go read that before, understanding that section. Also in this problem, as you can see, we have control variables that are binary matrix. And using a mixed integer optimization doesn't really work with binary. So I had to go first to use real numbers, and then later on relax it first, use real numbers, and later on round these, get the max and round to the closest 1 or 0, and that was able to help me get a binary values at the end. Also, as you can see, we have so many formulas. Translating that to something that you compute, it's going to be very intensive if you just do iterations and all of that. So there's a section in the paper trying to formulate the problem into using linear algebra to matrices, so we can utilize, do matrix multiplication and matrix, all the different types of, to make it efficient for calculation optimization. That's pretty much it. If you got time, I can show you the code. If not,
Yeah.